Hey kiddos and kiddas, it's Miss Lloyd, and we are looking at systems of equations today. So a system of equations is two or more equations with two or more variables. Today we're mostly going to be looking at two equations, which is two variables to keep it a bit simple. Our solutions are where the graphs of the equations cross, or where they meet. When we're solving by substitution, so typically we will solve by substitution, elimination, or graphing. When it comes specifically to substitution, we're wanting to get one variable alone in one of the equations. You can pick whichever one, and it doesn't matter what variable you pick. I always like to go for whichever looks easiest. So a variable that's already kind of alone, it doesn't have a coefficient with it, and I get the other variable on the other side. Once I have that variable solved for, I plug into the second equation, the equation that that variable was equal to. This is really difficult to go over in words. Once I have only one variable, I solve for that variable. I then do a back substitution into either equation to solve for the second variable. So we're looking for the solution to both variables, not just x, not just y, but both of them. So here's an example. I see on the top equation that the x and y don't have any variables, or sorry, don't have any coefficients. So that's what I'm going to try to solve for. And it looks like I could just add y to both sides and then have x completely by itself. And then of course 0 plus y is just y, so then I actually have both of them by themselves. So x is equal to y is equal to x. So in the second equation, I'm just going to pick a variable to substitute in. I feel like solving for x first, so where I have a y here in the second equation, I'm going to plug in what the first y was equal to. So because x and y are equal to each other, I can substitute them in for one another. I'm going to do some simplification. And I've got my x is equal to 3. Again, I need both variables, so I can plug this 3 back into the equation that we solved for here. And that means 3 would also be equal to y. Since x and y are equal to each other, if x is equal to 3, y is also going to be 3. And so I'm going to make sure that I have my entire solution set. So I show my x and my y, what they were both equal to in point form, because this is the point on the graph where these two equations would be crossing each other. There's also a situation where maybe we have a line passing through a parabola, or maybe two circles intersecting. Either way, we have situations where we have multiple equations. They may not be linear equations that are on the same graph, and we are looking at where they're crossing. So for this situation, I'm still going to use substitution, and I'm still going to start with the first graph here, just because it looks like I can very easily get y by itself. And now I can plug what this is equal to in for the y in the second part. I want to keep in mind the goal for this is to get only one variable, so have one variable that's the same. So I no longer have an x and a y, I only have an x value for this case. And so now I have a variable to solve for since I only have one. Now I have two solutions for my x value. That means that I'm going to have two solutions for my y's as well. I'm going to plug in each of these x's one at a time into any of the equations. Any of them will work. I think what's going to be easiest in this case is to plug it into where we had the y completely by itself. It's exactly the same as the first equation before I moved my 2x over. So because these are the same equations, it doesn't really matter if I plug it into the original or if I plug it into the new one. I just feel like the new one is easier because the y is already by itself. So I'm going to try plugging in -3 first, which was the first x that I had solved for. So now I have my first solution. So when I plugged in -3, I end up with -1 as my y value. So here's one solution. I'm going to do the same thing with my +2 now. So that means there were two places where these equations crossed or intersected at -3, -1, and 2, 9. This next bit is solving by graphing, and we're going to be using in my class a graphing calculator to do this. Because I don't have one on my iPad to kind of show each step by step, I'm going to be doing this with my students so that they can see each button that I'm pushing as I'm doing it. The last equation that I'm going to go over is a word problem. The cost of producing X units is C is equal to 1.5X plus 15,000. And the revenue obtained by selling X units is R is equal to 5X. How many items should be sold to break even? So the main question here is break even. And so to break even, that means that the cost and the revenue have to be the same. So we're putting in as much as we're getting back. That means that I'm setting both of these equations equal to each other. And here I only have one variable, and they only really want one variable. They're asking how many units sold in order to break even. And so I just have to solve for my X. I hope you guys found this helpful. If you did, please like and subscribe. If you have any questions, feel free to comment. And if you feel like this could be helpful for someone else, please feel free to share. Spread the love.